A high voltage is applied to the ball located on the end of the rod that is able to rotate about the axis O. This is an electrostatic pendulum. To the left of the ball, the grounded metal plate is placed. The ball starts to attract to its electric image in the plate and attains a stable equilibrium. Here, the results of measurements of the force of the electrostatic interaction between the charged ball in its image in the conducting plate are represented for different initial positions of the pendulum. As it is seen from the graph, the stable equilibria are on the left and on the right of the shaded region only. Moreover, for some parameters, there are two stable equilibria simultaneously on the left and on the right of the shaded region. The photos show two stable equilibria of the pendulum occurred at the same set of experimental parameters. The voltage applied to the balls is 15 kilovolts. Transition from one equilibrium position to another is possible at a weak external force. The slide shows the plots of the pendulum potential energy as a function of sine of the angle of the pendulum rod displacement from the vertical line at different values of the control parameters. It can be seen that depending on the values of these parameters, the pendulum can move from the initial position to the only equilibrium position, flip on the plate, or take one of the two stable equilibria. The dots indicate the equilibria shown in the previous picture. Here, the results of measurements of the force of the electrostatic interaction between the charged ball and its image in the dielectric glass plate are presented for different initial positions of the pendulum. Also, for some parameters, there are two stable equilibria simultaneously on the left and on the right of the shaded region. The pendulum motion has been simulated numerically. The charge applied to the ball was modulated harmonically. It was found that in the case when the pendulum has two stable equilibria at parametrical force, it can make chaotic oscillations. The slide shows the phase trajectory of the pendulum corresponding to the chaotic mode of the oscillations. The slide shows the angular coordinates of the pendulum as a function of time at the chaotic mode of oscillations and the corresponding Poincare section. The Poincare section has a form of unordered clusters of points, which is typical for the chaotic oscillations. When changing the values of the control parameters, the sustained regular parametric oscillations of the pendulum could be observed also. In this case, the Poincare section for the sustained mode of oscillations has a form of a regular figure, a circle.